In this video, we're going to look at some additional examples involving partial derivatives. So for this first example, we're going to look at the same function that we just found the partials for at the end of the previous video. So f of xy equals x cubed y squared minus 2x squared y minus 3x plus y. And instead of finding the partials, what we want to do here is we want to find equations for the tangent lines at the point 1, 1, parallel to the xy plane and parallel to the yz plane. So we want to find two equations of lines. Right? And so what we're going to need in order to do this is we're going to need to compute the derivative, the partial derivatives f sub x and f sub y at this point 1, 1. And that's going to give us the direction that these lines will be traveling at this particular point. So from the previous video, we saw that f sub x of xy was equal to 3x squared y squared minus 4xy minus 3, and f sub y of xy is going to be 2x cubed y minus 2x squared plus 1. Okay. And so what we need to do first is evaluate each of these derivative functions at the point 1, 1. So we're going to have f sub x of 1, 1, and that's going to be 3 minus 4 minus 3, so we'll get negative 4 there. And f sub y of 1, 1 is going to be 2 minus 2 plus 1, right, which is equal to 1. Right. Now, in order to determine the tangent lines with these particular slopes, we also are going to need to know the point on the graph of z equals f of xy at this point 1, 1. And so that z coordinate, that third component, is going to be f of 1, 1. So we're going to plug these numbers back into our original function. And so when we do that, we're going to get 1 minus 2 minus 3 plus 1, which is negative 3. Right? So using the first derivatives and the original function, we get these three values, negative 4, 1, and negative 3. So the first thing we're going to do is find the line parallel to the xz plane. Okay. Now we know to find a line we need to know two things. We need to know a point and we need to know a direction. Okay. Well, the point is easy. We just found that. We know that when x and y are both equal to 1, we know the z coordinate is f of 1, 1, which we just found to be negative 3. And so we know the point the line is going to go through is 1, 1, negative 3. We also need a direction vector for this line. And the way that we can think about that is to go back to the partial derivative of f with respect to x at the point 1, 1. We computed that to be negative 4. And so what that means is that if we look in the plane y equal to 1, thinking of y as constant, so in the plane y equal to 1, f sub x of 1, 1 is equal to negative 4. And so that slope, that negative 4, is the slope of the curve at that point in the plane y equal 1. And so that direction we can think of as a vector of 1, 0, negative 4. Right? And so we can think of the 1 and the 4 in the standard slope way. If we change x by 1 unit, the z coordinate will change by negative 4. That's what we mean by the slope of negative 4. And the reason the y coordinate of this direction vector is 0 is because in this curve, the curve lies entirely in the plane y equal to 1. So however far you move along the graph, the y coordinate does not change. Right? It has no change in the y direction, so that coordinate will be 0. So in this case, the line we have our point, we have our direction. And so if I want to call this line maybe L sub 1, of t, so this is a vector function. All right, we know this is going to be the point 1, 1, negative 3 plus t times our direction vector 1, 0, negative 4. And so when we combine this, we get the function 1 plus t, 1, and negative 3 minus 4t. Right, so this is the line parallel to the xy plane that's tangent to the curve at the point 1, 1. Right. Now for the other line, we're going to do something very similar. So now we want the line parallel to the yz plane. Well, we still have the same point. The point's not changing. So the point's going to be 1, 1, 3. Or, sorry, 1, 1, negative 3. And for the direction vector, we're now thinking of this curve lying on the plane x equal 1. And so since it's on the plane x equal 1, it's the direction that it's moving in the x direction is 0. So our x coordinate is going to be 0. And we found our partial derivative with respect to y value was equal to 1. So we can think of 1 as 1 divided by 1. So if we move 1 unit in the y direction, that moves 1 unit in the z direction. Right? And so we have our point in our line or in our direction. And so this becomes 1, 1, negative 3 plus t 0, 1, 1. And so this is equal to 1, comma, 1 plus t, comma, negative 3 plus t. All right, so these are the two lines that we are looking for. We will also at times want to differentiate functions of more than 2 variables, so 3 variables, 4 variables, and so on. And while we don't have any kind of geometric interpretation of this, the same exact process applies when we have more than 2 variables. Right. So what I mean by that is that if we want a partial derivative with respect to a particular variable, we're going to think of all the other variables as constant and differentiate with respect to the indicated variable. All right, so for example, let's take a function of 3 variables, x, y, and z, defined as follows. So it's going to be x squared times the sine of yz cubed minus the natural log of x, y, z. All right, so this is our function. Now, of course, we can't graph this at all. We can't have any kind of geometric interpretation of our derivatives, but we can think of each of these derivatives algebraically or analytically. So if I want to compute the partial with respect to x, we'll do this one first. So this will be a function of 3 variables, x, y, and z. We're going to treat y and z as constant and differentiate f with respect to just x. So in the first term, I have x squared, which we know the derivative of that is 2x. And then the remaining part of that term, the sine of yz cubed, does not involve x. And so we want to think of that as a constant. And so this just gets multiplied by 2x. Right, and now the second part, the natural log, we do have inside the natural log a multiple of x. Again, we're thinking of y and z as constant. So the derivative of natural log of x, y, z is going to be 1 over x, y, z. But then by the chain rule, we want to multiply this by the derivative of x, y, z, which, because y and z are constant, is just yz. Right? And so if we wanted to, this is not absolutely necessary, but we could simplify that at the end. In this case, it makes a lot of sense to simplify this, because this just becomes 1 over x. Right? The y and the z cancel. Right, so this is our partial derivative with respect to x. So now let's look at the partial derivative with respect to y. So now we're going to think of x and z as fixed quantities and think of y as our variable. So for the first term, x squared is a constant, so we're going to just keep the x squared intact. But now sine of yz cubed has the variable y involved. So we have to differentiate this using the chain rule. So derivative of sine is cosine. So we have cosine yz cubed. And then we need to multiply by the derivative of yz cubed. And so in this case, that means multiplied by z cubed, because that's a constant being multiplied by y. So the derivative of our first term is x squared cosine of yz cubed times z cubed. And then for the second term, the part with the logarithm, we get something very similar as in the first partial derivative. We get 1 over xyz multiplied by xz, and those cancel, so we're left with 1 over y. And lastly, we can do the partial derivative with respect to z. Right, so in this case, again, x squared is a constant. And we have to differentiate sine of yz cubed. So that'll be cosine of yz cubed. And then the chain rule, in this case, it's a little bit different. We have to multiply by the derivative of yz cubed, which will be 3yz squared. And then again, 1 over xyz minus, or 1 over xyz multiplied by xy, and that yields 1 over z. Right, so I went ahead and simplified that here. Right, and so this particular second derivative, or this particular partial derivative with respect to z, is this function here. Now notice that other than the part with the logarithm at the end, I really didn't simplify this. For example, just because it's here easily to write on, notice that if you wanted to, you could put this in kind of a more standard form of 3x squared y z squared cosine yz cubed. Right, so this is kind of the what you might call the simplified version, where we combine all the variables together and then all the other functions together. In this course, I honestly do not care how you leave your answers. The goal of these kind of things is to be able to compute the partial derivatives. Eventually, we'll want to use the partial derivatives to do other things. And so when we do that, then of course it probably benefits you to rearrange them in a nice fashion. But if we're just looking to find the partial derivatives, then no simplification is required. So if you'd like to try a problem like this, you can try this one, f of x, y, z. And let's say it's going to be sine of x over 1 plus y plus z to the 100th power. Right? And go ahead and compute the derivatives of with respect to x, y, and z. And I'll go ahead and write them down here, and I'll use the del notation for this one, just to vary it up a little bit. But this one should be cosine of x plus 1 over y times 1 over 1 plus y. Del f del y should be, I'm going to go ahead and simplify this one, despite what I just said a few seconds ago about not having to simplify, but just so that you can easily get your answer in the same form as mine. So negative cosine x over 1 plus y multiplied by x over 1 plus y squared. And of course, del f del z is probably the easiest one here, 100 z to the 99. Right? So try this one, confirm you have the right answers, and then you can go on to the next part of the video. So our last example here we'll look at the idea of implicit partial differentiation. So from Calculus 1, you probably remember implicit differentiation. This is the technique that's needed when we have y as an implicit function of x, meaning we have some equation involving x and y, but we can't solve it for y explicitly. We can't write it as y equals a function of x, oftentimes because the y is not a function of x. And so we can do the exact same thing in functions with more than one variable. So in particular, if we have a function with an equation with three variables, x, y, and z, we can always think of z as an implicit function of x and y. And so if we do an implicit differentiation, it works exactly as it did in Calculus 1. It's an analogous technique. And so let's look at an example. So let's say we wanted to find del z del x and del z del y if x cubed plus y cubed plus z cubed plus 6xyz is equal to 1. Right, so this is an implicit function of z. Because we have a z cubed and the 6xyz term, we cannot write this function in the term z equals some function of just x and y. And so we really, if we want to find the derivative here, we really don't have a choice but to use implicit differentiation. Right? And so we're first going to look at del z del x. So we'll focus on that one first. And so if you remember how implicit differentiation worked in two variables, we go through and we differentiate each term with respect to the variable in question, so in this case an x. And whenever we differentiate z or some function of z, we're going to throw in a del z del x, or in Calc 1 you might have used the z prime or an x or y prime when you differentiated a function of y. So we're just going to go along the equation, each term differentiate with respect to x, and throw in a del z del x whenever we differentiate a term involving z. So the derivative of x cubed with respect to x is 3x squared. The derivative of y cubed with respect to x is 0 because y is a constant. The derivative of z cubed with respect to x will be 3z squared. But then because we just differentiated a function with z, we need to throw on a del z del x. That's really just the chain rule of one variable calculus. Right? And then we get to the term 6xyz. And so this one is sometimes a little confusing. We really want to think of 6xyz as a constant 6y times xz. And so we have a product there, that x times z, and z here we're thinking of as a function of x implicitly. So when we differentiate this, we're going to need to use the product rule. Right? And so to do that, we're first going to differentiate x and leave z alone. So we're going to have 6y, derivative of x is 1, and we'll leave z alone. So we get 6yz. And for the second part, we're going to have 6y, and then x is going to be left alone. So we're going to have 6xy. And then we differentiate z, which is del z del x. And then all of that is equal to the derivative of 1, which is 0. Right? Now in this equation, I have two terms that have a del z del x. And so the strategy for solving this in Calculus 1 was to isolate those two terms on one side, put the non-del z del x terms on the other, and then factor out this del z del x and solve for it. And that's exactly what we're going to do. It's exactly what you did in Calculus 1. So if I keep the del z del x terms on the left side of the equation, I'm going to get 3z squared del z del x plus 6xy del z del x. And that's going to equal negative 3x squared minus 6yz. when I subtract those two terms to the right side. On the left side now, I can factor out a del z del x. And then to actually solve for del z del x, which is what we're trying to do, we just divide both sides by this quantity 3z squared plus 6xy. So our derivative del z del x, that partial derivative, is going to be negative 3x squared minus 6yz all over 3z squared plus 6xy. And so this is del z del x. If we wanted to find the slope of a tangent line in this direction, we could substitute the points, the coordinates for the point x, y, z that we're interested in into this equation and get that slope. Now we also want to find del z del y for this particular function. And I'm going to leave this one to you to try. Right? The same ideas as the first part. Differentiate every term with respect to y. And whenever you differentiate z, you need to throw on a del z del y to have its derivative there. And then solve for del z del y in that equation. And what you should get, I'll go ahead and give you the answer so you can check yourself. You should get negative y squared minus 2xz all over z squared plus 2xy. All right, so this is del z del y. All right, so try this. Make sure you remember how implicit differentiation works.